This unit, we took what, 2 weeks on?
Yes.
We took 2 weeks on it because this only counts for 4% of your test. I have never seen an electrostatics FRQ, which makes me suspicious it might pop up. And if it does, that's something you should absolutely knock out of the park, because it's probably going to be using the instrumentation we use in class, like the electroscopes or the Leyden jars. Okay. What's that?
What other thing would it use a Van de Graaff?
Nope. They don't use Van de Graaff generators is because Van de Graaff generators is not something you'd find in every physics lab. Yet. So they tend not to use any equipment not cheaply found. Okay, so we got the electrostatics unit. When I do this concept map, I'm just going to do it linearly, kind of like just an outline, just because when I try to do some things with it with a concept map, that's when the board started to go crazy. So I'm just going to go straight down. I will scan this, all right, and put this on Schoology. Now, in case you want to put it the exact same way I've got it, that's fine. But I don't think you need to. What's the unit? Electrostatics. So when it comes to electrostatics, one of the first things we talked about is what parts can and can't move. Parts can move. Electrons. All right. So electrons move only. Can't move the protons because that's nuclear reaction. Neutrons we don't even talk about in this class. It's electrons move only. And specifically when they say electrons, we're talking about the free electrons. All right. So it's free electrons, or sometimes it's mentioned as excess electrons. Electrons move in. We talked about two types of materials. What are the two types of materials we talked about? Conductors and insulators. So we got conductors. What's the definition of a conductor? Allows electrons to move, right? They can freely flow through them. So most conductors we talk about in this class are what type of materials? Metals. That's pretty much it. So they usually use iron or aluminum or steel, just some sort of metal. Okay. Look at something else up in there. Oh, conductors. We also say that these electrons can dynamically flow. So that's a little bit of a vocab word. Dynamic meaning they can move easily. You don't see this too much right now for this unit, but for next unit we do electricity. Electricity is where electrons are in constant movement. They're dynamic, all right? Which is why wires are made out of metals and not out of like rubber or plastic or anything like that. Okay. When you look at a conductor, let's say a conductor is standing on an insulating stand. What does, and let's give it a charge of, let's say, -4. What does that charge look like? Well, since it's a conductor and allows those electrons to easily move, those electrons are going to move as far away as possible. Okay? And we're going to go spread out. Cool? Not too bad. What's the other type of material? Insulators. Not Thursday. Let's try that again. There we go. So you got insulators. Does not allow electrons to move. What's the word that they like to use for that specifically, though? Restrict. All right, that's the word they like to use in there frequently, so it restricts electron movement. What type of materials they like to use for insulators? Rubber, glass, PVC, wood, most woods, plastic. Okay, either A, they're going to tell you it's a conductor or insulator, or they're going to be something that's obviously one or the other. What we don't talk about in this class are semiconductors, just because that deals with some very specific physics, but you also need to understand a little bit more depth in chemistry.
Wait, so that won't be in our test at all?
No. Okay. I know it's the Triboelectric Effect. It's talked about a little bit in your con videos. I would say that's probably not going to show up on your test. That's pushing it. Okay. So restricts electrons' movements, and this is what we call static electrons. All right, they do not move. So if I've got an insulator, and we'll give this a charge of -4. Those electrons are going to stay where they were dumped off at, or where they were created. So if I charged only one side of this sphere, those electrons could be stuck all on one side. They will not spread out evenly. Cool. Next thing we talked about was electrostatic force. So what causes these electrons to move? So electrostatic force, K Q1 Q2 over R squared.
Well, I have a question about
Yep.
what we just did with static.
Yep.
So, like, for them to be in that position, they would have had to, like, replace them?
Yeah, so like say if we rubbed the rabbit's fur only on one side.
Oh, then they would stay there.
Absolutely.
Okay,
So
but
when
if
you're
they're already scattered, they'd stay scattered.
Yes. So when you were doing the PVC pipe and you're charging, usually only one end of that PVC pipe was charged. Your hand and whatever's around your hand still stayed neutral. Cool?
Yep.
All right. The only questions, the only reason I really bring that up is because every once in a while they'll give you a question that says, a conductor has a charge of blank. What does the electrons look like in it? So really this unit, if you understand what electrons do, what kind of forces they produce, and what the cause, or say what those forces then affect, you're probably going to be good for this unit. They like to throw in relationships though. So what is the relationship between electrostatic force and charge? What's that called? Direct. So it's a direct proportional relationship. All right. What about electrostatic force and your distance between the center of those two charges? Inverse squared, okay? So very often what I'll see is they just like those proportionality questions we practiced. If I doubled the force, or if I doubled the distance, what would that do to the force? So on and so forth. I don't see too many questions actually pertaining to this, using that in depth, because that's more of a physics 2 concept. They kind of just look at relationships here and call it done. Which makes me suspicious that now they're going to start doing that. So if there's anything that, as I'm going to look at your standards, I imagine every once in a while they like to throw something tricky. I'll probably have those tricky things figured out before we take our mock exam. For example, 2 years ago they did resistivity, which is something that most physics teachers don't even get to. And it was one FRQ dealt with resistivity. It was rough. No, it's not something that close to, but we'll get there.
We're going to talk about it?
We will. We're going to do everything. We're going to do a Play-Doh lab. You're going to find the resistance of Play-Doh. I wouldn't recommend it. It's Play-Doh. All right. Your job when it comes to this is understanding why electrostatic force has absolute value signs around itself. Okay. Oh, I'm going to go back up a little bit. So why does this have an absolute value sign? Your job is to understand the direction of which those forces are. Okay. So if I call all these charges the same, the force of 1 onto 2, we'll call that 1, is going to be equal and opposite to of the force of 2 onto 1. Follow me there? See how one's going left, the other one's going right? It's still true if your signs are opposite. It's still going to be an attractive force, but 1 onto 2 is still equal and opposite of 2 onto 1. Okay. Common misconception is, what most people think is, if I double the charge, so if I make one of these 2Q, for example, some people think that you only change one force. Both forces are then doubled. Okay. Well, you could just look at the formula for reference. You're looking at, you multiply the two charges together. Come on, there we go. So the same reasoning if we look at gravity, because often electrostatic force and gravity are thought to be, gravitational force to be similar. If I double my mass, I've doubled the force pull of me downwards. Does that make sense? But I'm still pulling the Earth up with the exact same amount of force. Now, if I get as big as the Earth, all right, then the forces we pull on each other are still equal and opposite. Does that make sense? Cool. I think it's about forces, all I want to say. That's it. What's the law? We talked about that. What's the law we talked about in this unit?
Conservation of charge.
Law of conservation of charge, which is often written as LOCC sometimes. So law of conservation of charge, meaning charges, all right, cannot be created or destroyed. They can only transfer. So when it comes to this, I often see just two objects have some sort of initial charge. Let's call this plus 12. Let's call this one plus 6. When they come in contact with one another, what's the two charges going to do between them? I'm just going to add. And then when they're separated again, each charge is going to be, what, 9? What I have seen from time to time is compare the electrostatic force before the two objects touch and after the two objects touch. What's 6 times 12? 72. What's 9 times 9? 81. Are those forces going to be the same? No. Okay, so we could play around with the numbers here. And so it's not always going to be an increase in force. Sometimes it's a decrease in force. So you have to figure out, what does the charge look like beforehand versus afterwards? Well, if we keep the radius the same and we keep K's constant, so the electrostatic force here will be proportional to 72. Electrostatic force here will be proportional to 81. Those are not the same. So they're going to interact just a hair bit differently. Cool? So we could say that the electrostatic force between these two particles increased. Follow me there? Don't try to find a pattern there, because what if one was negative 6? That would give you 6 here. You separate it. That means your electrostatic force would be 72 compared to 9. So it means that force went downwards. Cool? So just do me a favor. Draw it out. Multiply the two numbers, probably looking good. Cool? That's the only really tricky ones I see on these types of on your test is, what do the relationships do before and afterwards? And I'm not going to say you guys do a good job of it, but you guys just don't write anything down when it comes to test time, and I can't tell what you did wrong. 9 times out of 10, I'm willing to bet you guys do better if you drew some pictures out. Okay, law of conservation of charge, done there. What are the two modes in which we can transfer electrons in this class?
Induction and conduction.
Conduction and induction. I'm sure there's other ways you could transfer electrons. Look in chemistry, bonding, and whatnot. But the two we talk about in this class are these two here. Conduction have to do what? Touch. Which means these are going to be no touchy. When it comes to conduction, what causes the electrons to move? Well, let's say electrostatic force causes movement. What about induction? It's still the same thing. So electrostatic force on both of these cause electrons to move. We're going to do some picture examples here in a second about what charges look like and who comes out on top. I'm going to be very specific on how I draw these. So if I bring, let's do blue. Try to do blue. Yeah. My finger's now blue. Okay, if I bring a positive charge near a sphere, what causes to that sphere? Let's call that sphere initially neutral.
The left side is negatively charged.
Alright. This is looking ugly real quick, so I'm going to clean that up a little bit. Alright, play nice. I have to X-nay the colors for now. So if we bring the sphere nearby, negatives go towards the left because it's an attraction. Positives go on the other side.
Well, don't they stay where they are?
They stay where they are, but they kind of face the other direction. So we really just think of the electrons move closer, causing the other side to be positive. Is this object still neutral? Yes. What type of material is this object?
Yeah, conductor.
Has to be a conductor, right? If it was an insulator, it wouldn't work. So when we did your pop cans, we're trying to get those pop cans to roll. If we had a plastic pop can, it wouldn't do anything. Okay? Here's the one thing that's very, 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 very important. You cannot have an unequal amount of positive and negatives if the object is still neutral. So here's what I mean by that. If I brought this positive nearby, and then I wrote this as negative, what am I saying for this object right here? It is negative. It's not neutral anymore. So if the object's still neutral, you have to draw the same number of positive and negatives on both sides.
Would it matter for your object?
What's that?
Would it matter for like the positive object that you like bring in here? Does it matter what charge that is?
It does a little bit, but we don't look at that too much. That's more of a quantitative rather than a qualitative answer. Okay. What happens if I were to flip this on its head? What if I would do it the other way around? So if I brought a negative rod nearby, the negatives would go to the other side, positives would go there. Okay. Both of them start out neutral. They stay neutral. Okay. Which one's this? Is this conduction or induction? Induction, all right. Okay. What if I then attached a wire?
The electrons go away. Positive.
Only when the negative.
Or in that rod.
For the negative rod, what do these electrons over here do?
Go through the wire.
They go away. What would happen here? Electrons come in. Because those electrons are being pulled by that positive rod as well. Follow me there? So if I were then to take the wire away, This object would be negatively charged, evenly distributed, right? This object would be positively charged, evenly distributed. Cool? Cool. And what was this called? Grounding, right? Is when you allow the electrons to do whatever they want to do to get out of a high stress situation. So right now, both of these situations, the electrons are in a high stress. By grounding it, we allow those electrons to do what they want to do and become less stressed. Cool? All right, I think that's all I want to say about that. You should be good on, if we take this and flip it, positive, negatives, please, please, please just draw a picture. Hopefully it'll help you figure it out. Last thing is, not Thursday again. I'm going to hit, there we go. What two types of instrumentation do we deal with a lot? Electroscopes and what? Leyden jars. So electroscopes often start off with a neutral charge and your leaves just drop downwards. However, if we induce, let's do it with the negative rod here. Oop. These electrons travel downwards and cause your leaves to spread out. Okay?
The electrons and the waves are trying to get away from each other?
Yes. The electrons in the metal sphere, when they're brought near, want to get as far away as possible, so they go to the leaves. The leaves don't have very much mass, and so those also separate as well. You notice if we touched it, though, you would have transferred some electrons. And the whole thing would have become negative. But those are, then again, it's evenly distributed. Cool? Same thing if you did with a positive rod. If you did the positive rod, what would happen?
The electrons would rush up to the top of the sphere and the positive charge in the bottom.
So we flip it on its head. Do this with a negative rod, or sorry, positive. That's easy to fix. All right.
I have a question.
The electrons would rush upwards, causing the bottom part to become positive. Yeah.
Okay, so when you can do something, can electrons come out of the thing into the
So if I were to, so right now we're just inducing a charge right now, right? If I were to touch the positive rod, that's what I was doing. If I were to touch the positive rod to it, I would cause some of those electrons to be pulled out, and then it would cause your Leyden jar to become positive. Cool.
You are inducing.
So if I were to see if I can, nope, it's not gonna let me do it. I'm not gonna try it. I'm just gonna scroll down. So that would be inducing it. If I were to touch the rod to the top of the Leyden jar, let's see if this works. It would lose some electrons and have an evenly distributed positive charge. And that's because some of your electrons are now in here. Follow me there. Cool. Questions? Comments? Concerns? All right, what was the other thing? Leyden jar. How did Leyden jar work? What was that inside layer?
Inside was
conductor.
Conductor. Middle layer was a insulator. Outside layer was a conductor. Okay. I have a reverse Leyden jar back there. I just found not too long ago, and it's an insulator, conductor, insulator, just to show you that it doesn't work. I was like, what's the point of this thing? And then I realized, oh, it's to show you it doesn't work. So how do you charge a Leyden jar? Via induction and then what?
Oh, grounded?
And grounding, right? If you try to charge a Leyden jar without holding that bottom layer, it wouldn't do anything. Your inside might become slightly negative or slightly positive, but unless you give somewhere for that other layer of electrons to move, it wouldn't do anything. So I'm going to scroll down, and then we'll see. So what'd you do? You took your Leyden jar.
This makes total sense.
I'm going to try to keep this color coded. And we brought that negatively charged PVC pipe nearby. So these electrons on the outside are now in a high stress situation. So we connected a grounding wire, and that allowed the electrons to leave. So you rub the electrons to it, you'd scrape it off, scrape it off, scrape it off. And so overall what you get is a Leyden jar.
The grounding wire is very huge.
Where the inside layer would be negative and the outside layer would be overall positive after you take that rod away again. So then to make the fun part of it, you would take your hand and then you would connect that inside layer to that outside layer and cause those electrons to redistribute evenly. Zaps it, or what's called, as the official term, a static discharge. And we now understand why static discharge is called that. The electrons are static. You are equaling out or causing the charge to no longer be there. Okay. Yep.
Is the grounding wire in our instance our hand or the table?
Could be either one as long as it's a conductor. So this grounding wire right here could be whatever is a conductor. And if it's an insulator, then those electrons aren't going to move on it. So if you put it on the tables are an insulator, but those metal shelves back there would work as a conductor.
Okay, so we're rubbing the thing on the circle, right?
Yeah.
So you produce the middle, or like the very inside.
What?
And that does induction because that has a
And that stays there
Mhm.
as an insulator, and then the outside was
Say it again.
the stuff that the electrons you pour into the middle stay there, right?
Yes.
Because
Those
they're surrounded by an
the electrons that are on that inside layer are already there. I'm adding more to it though.
Yeah, no, but the
Yeah.
ones you're adding stay there, right?
Yeah. 'Cause
Yes.
Yes, and then so the ones on the outside run away.
Correct.
Okay.
That's right. So just make sure we all understand, because she's asking good questions there, that as adding more electrons to that inside layer, we're putting electrons on the outside layer in a stress situation, and we gave them somewhere to run to. There's definitely a high stress situation on that
high stress.
I pushed it. I was pushing limits too far. Okay. Yeah. I think it's it.
Could you do a Leyden jar by induction? We do it by conduction.
And induction.
Yeah, be conduction and induction.
You can use like the very center, but that induces the outside.
Oh,
Yeah.
yeah, I guess. But what I'm asking is, so if you bring it near the center, would it work the same way either?
So there's no type of charge.
Say that again.
If you only bring the stick near the center and don't touch it, would it still work?
It would work if you want to do it both layers by induction, but it wouldn't be near as much. Yeah. I don't want to get into reasons to why, because that's gonna be a very long conversation.